Tonight, we're going to explore something that has driven mathematicians to nervous breakdowns, forced physicists to tear apart their most successful theories, and quietly underlies some of the most dangerous and most beautiful truths about the universe we live in. Infinity, not infinity as a poetic concept, not infinity as a way of saying very, very large, not infinity as shorthand for something so big we stopped counting, the actual mathematical, physical, cosmological object called infinity, the thing that appears in the equations of general relativity and signals something is catastrophically wrong, the thing that quantum mechanics encounters and must laboriously subtract away to get sensible answers. The thing that Georg Cantor spent his life studying and which led him to spend the final years of his life in a psychiatric institution. The thing that appears to exist in our universe right now in ways that most people have never been told. Infinity is not abstract. It is not safe. It is not just a symbol at the end of a number line. It is the universe's most confrontational property, the place where human intuition breaks down completely, the place where the rules of arithmetic stop working the way you expect, the place where something can be simultaneously the same size as something else and also infinitely smaller than it. The place where you can remove an infinite number of things from an infinite collection and end up with the same amount you started with. And it is not contained safely in mathematics textbooks. It lives in black holes. It may live in the structure of space itself. It may be the literal extent of the universe. It shapes what is and is not possible for any civilization anywhere. And it comes in sizes. Not one infinity, many, infinitely many infinities, each one incomprehensibly larger than the last. By the end of tonight, you're going to understand why the simple question of whether infinity is real has occupied the greatest minds in mathematics and physics for over a century. Why the discovery that there are different sizes of infinity was one of the most psychologically destabilizing ideas in intellectual history. Why infinity appears in our best physical theories in places that terrify physicists. And why the universe being infinite would mean something so strange that most people are never told what it actually implies. 7 truths about infinity that are genuinely, physically, mathematically, cosmologically terrifying. Not dramatic for the sake of drama, terrifying in the sense that they reveal how different reality is from everything your intuition prepared you for. Before we begin, if these questions about the nature of mathematics and what it says about reality are the kind of thing that stays with you, hit like or subscribe. It helps us reach more minds that want to sit with ideas like this. Now, let's begin. The year is 1891. Georg Cantor, a German mathematician at the University of Halle, publishes a short paper that contains one of the most elegant and most devastating arguments in the history of human thought. He calls it the diagonal argument. In 2 pages, he proves something that should be impossible. There is more than one infinity, not just slightly different amounts of infinite things. Fundamentally, qualitatively, provably different sizes of infinity. Infinities that cannot be put into any correspondence with each other no matter how cleverly you try. An infinite hierarchy of infinities, each one so much larger than the previous that no function, no mapping, no mathematical trick can bridge the gap. Cantor had spent years before this paper working on the foundations of mathematical infinity, and the mathematical community had mostly resisted him. The great mathematician Henri Poincaré called Cantor's work a disease from which mathematics would eventually recover. Leopold Kronecker, one of the most influential mathematicians of the era, called Cantor a corrupter of youth and a mathematical crank. The resistance was not just professional disagreement. It was visceral, almost personal, the reaction of minds confronting something their intuition refused to accommodate. Cantor pressed on. He developed a complete theory of infinite sets, infinite cardinal numbers, the transfinite arithmetic that described how different infinities related to each other. He mapped out the hierarchy of infinities with the same rigor that other mathematicians applied to ordinary numbers. And he suffered for it. He experienced severe depression. He was repeatedly hospitalized in psychiatric institutions. He died in 1918 in a sanatorium, still convinced of the truth of his discoveries, which by then were beginning to be accepted by the broader mathematical community. His discoveries were not wrong, they were right. And they were the beginning of the terrifying truth about infinity. The first terrifying truth. There are different sizes of infinity, and they cannot be compared the way you think. Here is what Cantor proved, stated as plainly as possible. The counting numbers 1, 2, 3, 4, 5, continuing forever, form an infinite set. Call this infinity the smallest infinity. Mathematicians give it the name Aleph Null, the first letter of the Hebrew alphabet, with a subscript 0. The even numbers 2, 4, 6, 8, 10, also continuing forever, also form an infinite set. How big is this set compared to the counting numbers? Your intuition says smaller. The even numbers are a subset of the counting numbers. For every even number, there is a corresponding odd number. The counting numbers contain all the evens and all the odds, so the counting numbers should be twice as big as the even numbers. But Cantor showed this intuition is wrong. To compare the sizes of infinite sets, you have to count whether you compare them up 1 to 1 with nothing left over, and you compare the counting numbers with the even numbers perfectly. Pair 1 with 2, pair 2 with 4, pair 3 with 6, pair 4 with 8, and continue indefinitely. Every counting number gets paired with exactly one even number. Every even number gets paired with exactly one counting number. Nothing left over on either side. By this measure, these two sets are exactly the same size. This is counterintuitive enough, but it gets worse. What about all the fractions? Every number expressible as a ratio of two whole numbers, 1/2, 1/3, 2/3, 17/43, every fraction imaginable, positive and negative and 0. There are infinitely many fractions between 0 and 1 alone. Between any two fractions, you can always find another fraction halfway between them. Fractions seem much more numerous than whole numbers. Cantor proved they are the same size. He devised a clever scheme for listing every fraction in a sequence, matching each fraction to a whole number. The rational numbers and the counting numbers are the same size of infinity. But then Cantor asked about the real numbers, every number on the number line, not just fractions, but also the square root of 2 and pi and every other irrational number. The numbers whose decimal expansions never repeat and never terminate. These are the points on a continuous number line, and he proved these are a larger infinity. His diagonal argument is devastating in its simplicity. Suppose someone claims they have a list of all the real numbers between 0 and 1, each paired with a counting number. Take the first decimal place of the first number on the list, the second decimal place of the second number, the third decimal place of the third number, and so on down the diagonal of the list. Now change each digit, replacing every one with a 2 and every other digit with a 1. You have constructed a number that differs from every number on the list in at least one decimal place. It is not the first number because you changed the first decimal place, not the second because you changed the second, not the nth because you changed the nth. Your supposedly complete list of real numbers does not contain this number. The list is incomplete. No list can be complete. The real numbers cannot be put in correspondence with the counting numbers. The real numbers are a larger infinity. Call it Aleph 1, or the cardinality of the continuum. It is strictly, provably, irreducibly bigger than Aleph Null. And there are larger infinities still. Cantor proved you can always construct an infinity bigger than any infinity you have by taking the set of all possible subsets of that infinity. The set of all subsets of the counting numbers is bigger than the counting numbers. The set of all subsets of the real numbers is bigger than the real number. The hierarchy extends without limit, an infinite tower of infinities, each one incomprehensibly larger than the previous. This is terrifying, not because it is complicated, but because it reveals that your intuitions about size and quantity and comparison, intuitions that work perfectly in every ordinary situation, are completely unreliable when applied to infinite collections. The word infinity does not name one thing. It names an endless tower of distinct mathematical objects. And we have barely begun to understand what this means for the physical world. The second, terrifying truth, infinity, appears in our best physical theories and signals. Something is broken. When infinity appears in a physical calculation, it is almost never good news. In the early days of quantum electrodynamics, the quantum mechanical theory of light and matter, physicists tried to calculate the precise properties of electrons, the mass of the electron, the charge of the electron, the way it responds to electromagnetic fields. They set up the calculations using the most sophisticated mathematical tools available, and the calculations kept returning infinities, not large numbers, not numbers too big to write down conveniently. Actual infinities, the self-energy of the electron, the energy contained in the electromagnetic field that the electron generates around itself, came out as infinite when the calculation was done the straightforward way. This is physically absurd. An electron with infinite self-energy would have infinite mass. Electrons manifestly do not have infinite mass. We know their mass precisely. Something was catastrophically wrong with the theory. The resolution, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga in the late 1940s, is a procedure called renormalization. The infinities in quantum electrodynamics can be systematically identified and absorbed into redefinitions of measurable quantities. You do not claim the bare, unrenormalized electron has a finite self-energy. You acknowledge that what you actually measure is always the electron interacting with its own field. You absorb the infinity into a redefined physical mass and charge. After renormalization, every specific, measurable prediction comes out finite and extraordinarily precise. Quantum electrodynamics is currently the most precisely tested theory in all of science. Its predictions match experiments to 12 decimal places. It works magnificently, and it works only because physicists found a way to hide the infinities in a mathematically controlled way. This is deeply unsatisfying. Not the accuracy of the predictions, the fact that the theory contains infinities that have to be systematically swept away to make sense. Most physicists believe that the infinities are signaling that quantum electrodynamics is not the final story, that at some very small distance scale, some new physics enters that removes the infinities and makes the calculation finite from the start. But we do not currently know what that physics is. And then there is general relativity, Einstein's theory of gravity, the most beautiful and most complete theory of gravitation ever constructed. General relativity predicts black holes, gravitational waves, the expansion of the universe, the bending of light by massive objects, the slow ticking of clocks in gravitational wells. Every prediction it makes has been confirmed with extraordinary precision, and it predicts infinities. At the centers of black holes, the equations of general relativity produce a singularity, a point of infinite density, infinite space-time curvature, infinite everything that can be infinite, not a region of very high density that we are approximating as infinite for convenience, an actual mathematical infinity in the equations that describe the physical world. No physicist believes the singularity is real. Every physicist believes the singularity is telling us that general relativity breaks down at the enormous densities and curvatures near a black hole's center. Something else is happening there, something described by a theory that correctly unifies quantum mechanics and general relativity. We do not have that theory. The singularity is the universe shouting at us that our best understanding is incomplete. The Big Bang is another singularity. Run the expansion of the universe backward in time using general relativity, and you arrive at a moment of infinite density and temperature at the beginning. Again, physicists universally believe this singularity is signaling the breakdown of general relativity at very small distances and very high energies. The true description of the universe's origin requires quantum gravity, which we do not yet have. Infinity appears in our best physical theories wherever those theories are pushed beyond their limits, not as a sign that infinity is physically real, as a warning signal, a red flashing light that says the theory is being applied outside its domain of validity. The universe is not infinite in density at the center of black holes. The equations that describe the universe are giving us infinities because the equations are wrong in that regime, not because the universe is actually infinite. But there is another kind of infinity in physics that is not a warning signal. That may be real. The third, terrifying truth. The universe may actually be infinite, and that implies something monstrous. The question of whether the universe is spatially infinite is not answered by any current observation. We can observe the observable universe, the region from which light has had time to reach us since the Big Bang, a sphere about 46 billion light-years in radius. Beyond that horizon, we cannot see. We do not know what is there, whether the universe continues beyond our horizon, and if so, whether it continues forever, is genuinely unknown. But the leading cosmological models say it probably does continue, and probably forever. The universe appears to be spatially flat. Measurements of the cosmic microwave background tell us that the geometry of space on the largest observable scales is not curved the way a sphere is curved or the way a saddle shape is curved. It is flat, like a sheet of paper, to within the precision of our measurement. And a spatially flat universe, in the simplest models, is an infinite universe. Flat here does not mean two-dimensional. It means the geometry of space on the largest scales is Euclidean. Parallel lines do not converge. The angles of triangles add up to exactly 180 degrees. The universe extends in every direction without curving back on itself. And if it extends without curving back on itself, it extends forever. This is already a profound result. But here is the terrifying implication that most people are never told. If the universe is spatially infinite, and if the universe has roughly the same density of matter everywhere, then the universe contains an infinite amount of matter, an infinite number of atoms, an infinite number of galaxies, an infinite number of stars, an infinite number of planets, and an infinite number of planets means an infinite number of planets where conditions are similar to Earth. An infinite number of those planets mean an infinite number of planets where life evolved. An infinite number of life-bearing planets means an infinite number of planets where intelligent species arose. An infinite number of intelligent species means an infinite number of civilizations. And here is where it becomes genuinely monstrous. The number of distinct physical configurations of matter in a region the size of our observable universe is finite, enormous, but finite. A specific calculable number, something like 10 to the power of 10 to the power of 120. The Bekenstein bound we discussed in previous videos. A number with more digits than there are atoms in the observable universe, but a finite number. If the universe is infinite and contains an infinite amount of matter, and the number of distinct configurations is finite, then by pure probability, every possible configuration must be repeated repeated infinitely many times. Somewhere in the infinite universe, there is a region of space identical to our observable universe, with the same galaxies, the same stars, the same Earth, the same history, the same you. And there are infinitely many such regions, not possibly, not theoretically, with certainty. In an infinite universe with finite configurations, repetition is mathematically inevitable. This means there are infinitely many exact copies of you right now, having this exact experience in regions of the universe so distant that light from here will never reach them, and light from there will never reach you. They are beyond any possible observation, beyond any possible communication, but if the universe is infinite, they are there. The cosmologist Max Tegmark calls this the level 1 multiverse, and it is the most boring multiverse, the one that requires no exotic physics, no multiple quantum branches, no parallel universes in any dramatic sense, just the same universe, continuing indefinitely in every direction, with finite configurations repeating at finite intervals in an infinite space. The exact distance to the nearest region identical to our observable universe can be calculated. It is approximately 10 to the power of 10 to the power of 120 meters, a number so large it transcends description, but finite and guaranteed to exist if the universe is infinite. This is what infinity actually implies, not something vaguely large and awe-inspiring. Something with precise, calculable, deeply strange consequences for the structure of reality. Consequences that cannot be observed but cannot be avoided if the universe is what the most straightforward interpretation of current evidence suggests it is. The fourth terrifying truth: you cannot escape infinity with infinite time. Here is a thought experiment that reveals something about the relationship between infinity and time that most people have never considered. Suppose you want to count to infinity, not to the largest number you can write down, not to some astronomically large number, but to actual infinity. How long would it take? The obvious answer is infinite time. To count to infinity, you would need to count forever. But consider something more surprising. Suppose you count the first number in 1 second, the second number in half a second, the third in a quarter second, the fourth in an eighth, each subsequent number in half the time of the previous. This is the mathematical series 1 plus 1, half plus 1 quarter plus 1/8, continuing forever. This series has a finite sum. It converges to 2. If you follow this schedule, you would count through infinitely many numbers in exactly 2 seconds. In a mathematical sense, you can complete an infinite number of tasks in finite time, provided the tasks shrink in duration fast enough. This is called a supertask, and it is not just a mathematical curiosity. It reveals something genuinely unsettling about the relationship between infinity and time, and about whether infinite processes can have completion states. A related problem is Zenos' paradox, formulated by the Greek philosopher Zeno of Elea around 450 BCE and never fully resolved to universal satisfaction. To cross a room, you must first cross half the room. Before you can do that, you must cross a quarter of the room. Before that, an eighth. The journey is composed of infinitely many steps. How can you complete infinitely many steps in finite time? The mathematical answer is that the series of distances converges. The infinitely many steps have a finite total length. You cross the room. Infinity and completion coexist. But here is where it gets troubling for physics. If supertasks are mathematically possible, are they physically possible? Could any physical system complete an infinite number of operations in finite time? The answer is almost certainly no. and the reason is deeply connected to the quantum nature of reality. Physical processes have minimum timescales. The Planck time, approximately 10 to the minus 43 seconds, may represent the smallest physically meaningful unit of time. No physical operation can be completed in less than the Planck time. This puts an absolute upper bound on how many operations can be completed in any finite duration. A physically realizable supertask would require operations that proceed at twice the speed of the previous one, without limit. Eventually, the operations would require less than the Planck time. The supertask cannot be completed in any physical universe. But this reveals something important. The mathematically infinite and the physically infinite are not the same thing. Mathematics can describe infinite processes that complete. Physics cannot implement them. The infinity that mathematics can handle does not map cleanly onto the infinity that physics can realize. And this tension between mathematical infinity and physical infinity runs through some of the deepest problems in science. The renormalization of quantum field theory, the singularities of general relativity, the infinite extent of a spatially flat universe. All of these involve questions about which infinities mathematics permits and which the physical universe actually contains. The honest answer is that we do not fully know. And the not knowing is terrifying, precisely because it matters for real physics, real cosmology, real understanding of what exists. Let's step back from the mathematics for a moment and think about what infinity means at the scale of exploration. The Voyager spacecraft, whose extraordinary journeys we have traced through this entire video series, have traveled for nearly 50 years and covered approximately 160 astronomical units, 14.8 billion miles, the most distant objects any human has ever sent anywhere. And here is the relationship between Voyager's journey and infinity. The observable universe is 46 billion light-years in radius. 1 light-year is approximately 63,000 astronomical units. The observable universe is therefore approximately 3 billion astronomical units across. Voyager has covered 160 astronomical units in 50 years. Even if the universe is only as large as what we can observe and not infinite, Voyager would need to travel for something like 1 followed by 30 zeros years to cross it, a number so incomprehensibly larger than the current age of the universe that the comparison is essentially meaningless. And if the universe is infinite, which the evidence suggests, Voyager is not traveling toward anything. It is traveling through an infinite medium in a random direction, making no progress toward any boundary because there is no boundary. The golden record aboard Voyager 1, which Sagan and his team created as a message to the cosmos, is drifting through space that may extend forever in every direction without limit. The golden record will never reach the edge, not because it is slow, because there may be no edge to reach. And in an infinite universe, the golden record and everything about it, the music, the images, the greetings in 55 languages, all of it is being duplicated in infinitely many other regions of the universe right now, encoded in the configurations of matter that repeat endlessly across infinite space. There are infinitely many golden records in the universe. Infinitely many Voyagers, infinitely many Sagans who made them. The unique gesture of a species reaching out into the cosmos is, in an infinite universe, not unique at all. It is infinitely repeated, And somehow, knowing that does not make the gesture less meaningful. It makes it more astonishing. That in an infinite universe of infinite repetition, conscious beings still experience their own reach toward the unknown as singular and precious. Infinity does not diminish the human project. It contextualizes it in a way no finite frame of reference ever could. The fifth, terrifying truth. Infinity makes probability incoherent. Here is a problem that keeps cosmologists and physicists up at night. In a finite universe, probability is straightforward. If there are 100 possible outcomes and you want to know the probability of one of them, you count. The answer is 1 in 100. You can assign probabilities to events, compare them, calculate expected outcomes, and reason about likelihoods. In an infinite universe, this breaks down completely. And the breakdown is not a technical issue that better mathematics might resolve. It is a fundamental problem with what probability means in an infinite context. Suppose the universe is infinite and contains infinitely many planets. How many of those planets have life? The answer might be infinitely many, or it might be infinitely many but a smaller infinity, or it might be a finite number. Without knowing the distribution, you cannot say. And even if you know the fraction of planets with life in any finite region, generalizing to an infinite universe requires assumptions that the mathematics does not uniquely determine. This is called the measure problem. In an infinite universe, or in an infinite multiverse, you need a measure, a way of assigning consistent probabilities to events. And there is no unique, obviously correct measure. Different, reasonable-sounding choices of measure give different probabilities for the same events. Some choices say that typical observers should find themselves in universes with specific properties. Other choices say typical observers should find themselves in completely different conditions. The eternal inflation scenario, which provides a physical mechanism for generating multiple bubble universes with different properties, runs into the measure problem acutely. Eternal inflation produces infinitely many bubble universes. To make predictions about what properties a typical observer should find in their bubble, you need to compare the number of observers in bubbles with different properties. But comparing infinities requires a measure, and the measure is not given by the physics. Different physicists proposing different measures get different predictions. The measure problem is not a peripheral technicality. It is the central obstacle to making empirical predictions from cosmological theories that involve infinity. If we cannot define what typical means in an infinite universe, we cannot test whether our universe is typical. We cannot check whether the theory is right. The physicist David Gross once said that the measure problem is one of the most important unsolved problems in theoretical physics. He may be right, and it is entirely a problem of infinity. Remove the infinity and the problem disappears. Retain the infinity and the problem seems intractable. But we cannot simply choose to remove the infinity. If the universe is infinite, it is infinite regardless of whether that is mathematically convenient. The measure problem is the universe's infinity confronting our desire to make predictions. The sixth terrifying truth. The infinity inside atoms was almost fatal for physics. The story of how physicists dealt with the infinities of quantum field theory is one of the most dramatic intellectual struggles in the history of science. And it is not over. When Paul Dirac combined quantum mechanics with special relativity in 1928 to produce the Dirac equation. He predicted the existence of antimatter before it was discovered. He also inadvertently opened a Pandora's box of infinities that would occupy the greatest minds in physics for decades. The problem is that quantum field theory describes the vacuum of space as filled with virtual particles, pairs of particle and antiparticle that pop into existence and annihilate. These virtual particles interact with real particles. The interactions affect the properties of real particles in measurable ways. But when you try to calculate these effects precisely, adding up contributions from virtual particles at all energy scales, the sum diverges. It runs off to infinity. Feynman, Schwinger, and Tomonaga solved this problem for quantum electrodynamics using renormalization. But Feynman himself was deeply unhappy with the solution. He called it a dippy process. He pointed out that you were essentially subtracting infinity from infinity and getting a finite answer, and that while the answer was correct, the process was mathematically ugly in ways that suggested the theory was not telling the complete truth about nature. Later developments extended renormalization to the other forces of nature. The weak nuclear force and the strong nuclear force were shown to be renormalizable. Renormalizable theories are those where the infinities can be systematically absorbed into a finite number of redefined physical parameters. Quantum chromodynamics, the theory of the strong force, is renormalizable. The electroweak theory is renormalizable. The standard model of particle physics is renormalizable. General relativity is not renormalizable. When you try to quantize gravity, to treat it as a quantum field theory, the way the other forces are treated, you find infinities that cannot be absorbed into any finite number of redefined parameters. You need an infinite number of counter terms to absorb all the infinities. The theory loses all predictive power. This is why quantum gravity is so hard. Not just technically hard, fundamentally, structurally hard in a way that no amount of computational sophistication can resolve. The infinities of quantum gravity signal that treating gravity as a quantum field on a fixed space-time background is wrong at the deepest level. Something different must replace it. String theory is one proposal. Loop quantum gravity is another. Neither is confirmed by experiment. The infinities of quantum gravity remain unresolved. The universe is telling us, through its infinities, that our understanding of space, time, and gravity is incomplete in ways we have not yet found the language to correct. The Voyager team, designing spacecraft in the early 1970s, did not need to worry about the infinities of quantum gravity. The physics they needed, Newtonian mechanics, orbital dynamics, the equations of motion for spacecraft and gravitational fields, are all finite and well-behaved at the scales they were working at. The infinities live at the Planck scale, distances of 10 to the minus 35 meters, energies of 10 to the 19th billion electron volts. Conditions so extreme that no instrument we have ever built can probe them directly. But they are there, hiding at the foundation, signaling something our theories have not yet learned to say. The seventh, terrifying truth. Infinity is what happens when mathematics meets its own limits. The deepest and most terrifying truth about infinity is not about the universe, it is about mathematics itself. In 1931, the Austrian mathematician Kurt Gödel published two theorems that shattered the foundational program of mathematics. The program, associated with David Hilbert, had aimed to establish mathematics on a complete and consistent set of axioms, to show that every mathematical statement could in principle be proved or disproved from those axioms, to make mathematics a closed, finished system. Gödel showed this was impossible. His first incompleteness theorem states that any consistent formal system powerful enough to describe basic arithmetic contains statements that are true but unprovable within the system. There are mathematical truths that cannot be reached from within mathematics itself. The system is inherently incomplete. His second incompleteness theorem states that no consistent formal system can prove its own consistency. Mathematics cannot prove, from within mathematics, that mathematics does not contain contradictions. These theorems do not use the word infinity, but infinity is at the heart of them. The unprovable statements that Gödel's proof constructs are statements about the infinite, specifically about what is and is not reachable by infinite sequences of logical operations. The incompleteness is a consequence of the way formal systems interact with the infinite. One direct consequence, proved by Cantor and shown to have deep connections to Gödel's work, is that the continuum hypothesis, the question of whether there is an infinity between the counting numbers and the real numbers, is undecidable. Not just unknown, undecidable from the standard axioms of mathematics. You can add an axiom saying the continuum hypothesis is true and get a consistent mathematics. You can add an axiom saying it is false and get a different, consistent mathematics. Both are equally valid. Mathematics cannot determine which is correct from within mathematics. The axiom of choice is similarly undecidable. The axiom of choice states that given any collection of non-empty sets, you can always choose one element from each. It sounds obvious. It is a statement about infinite collections, and its consequences are deeply counterintuitive. With the axiom of choice, you can prove the Banach-Tarski paradox, a mathematical theorem that says you can decompose a sphere into a finite number of pieces and reassemble them into two spheres, each the same size as the original. You have doubled the volume with no physical input. This is not physically realizable because it requires decomposing the sphere into non-measurable sets, mathematical objects with no definite volume, things that cannot exist as physical regions. But the theorem is valid mathematics. The Banach-Tarski paradox is infinity's revenge on intuition, a proof that objects that are the same size can be rearranged to produce two objects of the same size as the original, not by physical division, by mathematical decomposition into the infinitely intricate pieces that only mathematics can construct. These results together paint a picture of infinity as the place where mathematics confronts its own incompleteness, where the power of formal reasoning reaches its limits, where questions arise that no finite sequence of logical steps can resolve, where the universe of mathematical truth turns out to be genuinely larger than the universe of mathematical proof. And this matters for physics because physics uses mathematics. The equations that describe the universe are mathematical objects. If there are truths about infinity that mathematics cannot prove, there may be truths about the physical universe that physics, as a mathematical enterprise, cannot access. Not just unknown, unknowable from within the framework we use. Gödel's theorems do not say physics is incomplete. They say mathematics is incomplete. Whether physical reality is limited the same way mathematics is limited is a question we cannot answer. But the possibility that the universe contains truths that no sequence of finite reasoning steps can reach is not ruled out. The incompleteness of mathematics in the face of infinity is perhaps the most terrifying truth of all. Not because it prevents us from doing science. We have been remarkably successful at extracting truth from the universe using incomplete mathematics. But because it suggests that the map of mathematical knowledge, already infinite, is smaller than the territory of mathematical truth. And the territory of mathematical truth may be smaller than the territory of physical reality. We are navigating with an incomplete map of an incomplete map. What does all of this mean taken together? Cantor spent his life mapping the hierarchy of infinities and spent his final years in a psychiatric institution. Gödel proved mathematics cannot prove its own consistency and eventually starved himself to death out of fear of being poisoned, unable to trust the world outside his own mind. Boltzmann, who spent his life fighting for the atomic theory of matter and the statistical nature of thermodynamics, theories that required thinking about infinite numbers of particles and their infinite possible configurations, died by suicide in 1906, just as the scientific community was beginning to accept his work. These are not coincidences. Confronting infinity, genuinely confronting it rather than waving it away as just a very large number, takes something from the minds that do it. It requires accepting that the foundations of reality are stranger than any of us were prepared for. That size does not mean what we thought it meant. That probability does not work the way we expected. That mathematics cannot prove everything we want it to prove. That the universe is perhaps larger and stranger and more various than any finite mind can fully comprehend. And yet, the Voyager spacecraft, built with primitive computers and slide rules and physical intuition accumulated over centuries of careful observation, navigated to every outer planet in the solar system and beyond. The engineers did not need to solve the measure problem. They did not need to resolve whether the universe is infinite. They needed to solve differential equations, manage a power budget measured in watts, and calibrate instruments designed with 1970s technology. They succeeded beyond anyone's expectations. Not by understanding everything, by understanding enough, by working within the limits of what finite minds with finite tools can know, and doing extraordinary things within those limits. This is the human answer to the terrifying truth about infinity. Not that we can comprehend it, not that we can map it completely, not that we can resolve the measure problem or decide the continuum hypothesis or find a finite renormalization of quantum gravity, but that we can press forward anyway, understanding more each generation than the last, building instruments more sensitive than our predecessors, testing theories against reality with increasing precision. The golden record aboard Voyager was made by people who knew they could not fully understand the cosmos they were reaching into. Sagan knew the universe might be infinite. He knew the golden record might drift forever through an infinite space without ever being found. He made it anyway, not because he thought he could reach the infinite, because the reaching, however finite, was worth doing. This is what the terrifying truth about infinity actually means for creatures like us. We did not evolve to understand infinity. Our brains developed to track animals on African savannas, to recognize faces, to predict the behavior of other humans, to navigate environments that are always finite and usually small. The portion of our cognitive machinery that can grapple with infinity, that can follow Cantor's diagonal argument and see that it must be right, that can trace the implications of Gödel's theorems and accept their conclusion, is borrowed from machinery designed for other purposes and stretched to its limits. When infinity breaks our intuition, when the Banach-Tarski paradox makes no physical sense and we can prove it is mathematically true, when the continuum hypothesis is undecidable and we cannot say which answer is correct, when the measure problem makes probability meaningless in an infinite multiverse, we are not failing. We are succeeding at a task evolution never prepared us for. We are thinking about things that are genuinely beyond the natural scope of human cognition, using the imperfect tools of finite minds. The terrifying truth about infinity is not only that the universe may be infinite, or that infinity appears in our equations as a warning signal, or that different infinities cannot be compared the way we expect, or that probability breaks down in infinite contexts. The terrifying truth is that the territory we are trying to map, the full extent of mathematical and physical truth, may be genuinely and permanently beyond any finite mind's complete comprehension. And we map it anyway. One measurement at a time, one theorem at a time, one spacecraft at a time, one generation of scientists and mathematicians at a time, building knowledge that no individual can hold entirely in their head, distributed across civilizations and centuries, and the physical records we make of what we have found. The voyagers will drift through infinite space, or space that extends for distances that might as well be infinite, for billions of years after the last human mind has stopped wondering about them. The golden records they carry will endure long after the civilizations that made them. In an infinite universe, they are infinitely replicated and also unique. Both things are true simultaneously. Infinity allows both. We are finite beings in a possibly infinite universe, doing the finite work of trying to understand it and succeeding well enough to have sent 2 spacecraft to interstellar space with 68 kilobytes of memory and transmitters weaker than a refrigerator light bulb. That is not nothing. In an infinite universe with infinitely many possible histories, that is exactly what it is. Real, specific, ours. The terrifying truth about infinity is that it does not diminish what we have managed to understand. It reveals the full scope of what remains to be understood. The invitation is implicit in the terror. 7 terrifying truths. And every one of them is the universe showing us how much farther there is to go. Not close enough to say we have reached the end. Not close enough for any final answer. Just pressing forward in the vast, possibly infinite emptiness. Exactly as we should be.